Now, what I just said at the end of the previous session about there not being any questions at the end of the chapter 1 in the textbook by Davies, strictly speaking, that's true. But there are questions for chapter 1. I didn't realize that. They're in fact, all the questions for the whole book are found in an appendix at the back, Appendix F on exercise. I don't know if you can see that. But there are questions, and that was a bit of a surprise to me. I didn't realize it at the time. So there are in fact seven questions for chapter 1. I'll do 3 in this problem-solving session, which is a bit of a surprise for me. Now, the first one is quite long. It's like, you know, all this and up to here, so it's half the board. But it's conceptually important, historically important in the development of quantum mechanics. It's the so-called Compton effect. I'll say a little bit about Compton the guy, and then what he discovered. Compton was an American practical, experimental physicist, living, I think he did his work in what, 20s probably, 20s, 30s, that sort of time frame. And what he did actually was bounce X-ray photons off electrons and so forth. And they, in general, they would deflect. So, like you'd have here, say, an electron, and an X-ray photon would come in and bounce off and deflect. Now, in this case, in this particular problem, it's a special case. The photon hits the electron dead on, such that it bounces right back, right? And the electron gets a kick and it goes straight on. So everything's done on a straight line. There's no second dimension. Everything's done in one dimension. So it simplifies things. And he got the Nobel Prize for this, because if you think about, you know, what does that imply? What does that show? It shows that this photon, this X-ray photon, is acting like a bullet. Right? It's acting like a classical particle hitting another particle, and with the conservation of energy and conservation of momentum, you can actually, like, if here's an electron. Stationary, that's also as in the problem. So imagine where my fist is, that's this stationary electron, and a photon of a given frequency, say F1, hits this stationary electron head on, and then bounces back. It will have less energy, of course, because it's given the electron some energy, because it's given a kick. So this electron now moves off along the same line at at a particular momentum and energy. So the energy of the photon getting kicked back will be less. So its frequency will go down. Right. Remember, the energy of a photon is Planck's constant times the frequency, hf. So the frequency, when it bounces back, will be less, and hence its wavelength will be greater. And the point of this question is you're asked to calculate the difference in the incoming wavelength and the outgoing wavelength. So find some term for the difference of those two wavelengths using conservation of energy and conservation of momentum of the whole system, and everything's done on a straight line. So a one-dimensional case, which is simpler than Compton's more general two-dimensional case, where we've got the X-ray photon sort of bounces off and deflects, the angles. Then you have to do conservation in two dimensions, like the y-axis and the x-axis and so forth. It's a bit more complicated, but even so, it's still it's non-trivial. So all right, so here is your electron, little e for electron. I've got a minus here for its charge. That's a fairly typical symbol for an electron. If it's a positron, everything's the same except the charge, which will be positives, like the positive electron, you'd have a little e with a plus up here, but it's an electron. Okay, so it's not moving, so it's stationary, just sitting there. And a photon comes in at energy hf1, so it has a particular frequency f1. Okay, so it comes in, gives this electron a kick. So this little x here, this is like before and after. The before shot, the after shot. Right? So this little x here is the point of contact, point of collision, where the photon hits the electron. So the electron now is bouncing this way because it's been hit that way. It's been given a kick, and it'll have a certain momentum and a velocity. So mass, I could say this mass here is this m naught. I'll explain what that means in a minute. So this electron is now moving at a velocity v, and it has a mass m. And you're asked to show that the difference between the incoming wavelength of your photon and the outgoing, the bouncing back wavelength. So the difference between these two wavelengths is this quantity here, 2h over c m naught. Assuming conservation of energy and momentum. So as in classical mechanics. So in many respects it's a classical mechanical conservation type question. A lot of this, if you've done classical mechanics, a lot of this calculation will be fairly familiar to you, right? Although it's quite a bit of algebra, as you'll see. Alright, now let's see. This question assumes that you know some special relativity. So why don't I go off at a tangent a little and talk about that, because special relativity is very important for several reasons, and so important one of my dozen or so undergrad courses will be a thorough, quite a longish treatment, a course on special relativity, and the text that I will use for that course, I haven't decided yet what order to do all these undergrad courses, but there are about a dozen of them. And each one is considered to be a very important basis for the high level stuff at grad level. Now here's the text that I'll be using. It's called just Special Relativity. It's by French. That's the name of the author. And it's one of the MIT introductory physics series. So it's a bit old now. When did this one come out? 68. So it's from the 60s. But special relativity theory doesn't change much. It's pretty well stabilized. Okay, so the age almost doesn't matter. So that's the textbook that I'll be using, and it goes into all the various phenomena of special relativity, which is pretty weird stuff. Time flow depends on the observer, and you look at some other person flying past you, and you'll see their lengths shrink, and their time goes more slowly than your time, and their mass goes up compared, as you see it. All this weird stuff. And magnetism is a sort of a relativistic phenomenon from electricity. The speed of light is constant. You can't go faster than the speed of light. All this weird special relativity stuff from Einstein, the great genius who discovered this. Now, why is special relativity so important? Several reasons. It's the basis of general relativity, and that's graduate level stuff. And I will take you, definitely M1, M2. I think I go all the way up in general relativity. I think I go right up to PhD 2 level. So general relativity, very important, because what is one of the major thrusts of modern physics? The big dream is to unify the two major theories of modern physics, namely quantum field theory, it's quantum mechanics effectively, and general relativity, because those two topics, those two fields, speak very different languages, right? Quantum mechanics, that's all about quantized quantities. And general relativity is essentially classical. You know, it's deterministic, it's smooth, you know, you can have continuous values. They're just night and day relative to each other. So how on earth do you unify them? So yeah, that's one of the major challenges for modern physics. And the big hope is that string theory may do that. And there have already been some pretty major successes, like general relativity is a consequence of string theory. So you know, definitely some successes. Now, the other big thing that you need special relativity for is for quantum field theory, QFT, which I'll start teaching that at M1 level by the same guy that I'll be doing quantum mechanics at M1 level. The same guy, Mandel, M-A-N-D-L. So I will teach his I will use his quantum field theory text. I quite like Mandel, very clear, thorough. But the guy I really like is a German guy, a guy called Greiner, G-R-E-I-N-E-R, Greiner. And I'll be using nearly all of his textbooks. His textbooks are just famous in Germany. I mean, the whole generations of German theoretical physics students have been taught using Greiner's textbooks, and they're so famous they've been translated into English fairly recently, a decade or so, and they're starting to really have a similar reputation in the English-speaking countries, because they're just good. But they've all been good. They're really good. I'm impressed by Greiner and his texts. So anyway, special relativity needed to understand quantum field theory. And especially Dirac. Dirac was a British, very taciturn, hardly said anything, mathematical physicist. A lot of people think he's second, as a theoretical physicist, second only to Newton amongst the British theoretical physicists. And what Dirac did was to wed, so he combined special relativity and quantum mechanics, and created a relativistic, in other words, special relativity made, relativistic quantum